So, if we're going to talk about volcanoes, we're going to want to know why volcanoes form where they do. And in order to answer that question, we have to consider what conditions allow magma to form. First, consider that a decrease in pressure can actually lower the melting temperature of materials in the asthenosphere. This actually happens for all solid materials for the most part. Decreasing the pressure will lower their melting point. And it happens with rocks and minerals as well. So, decreasing pressure can lower the melting temperature, allowing rock to melt. Such a decrease happens if you've got a rift valley. There's less material exerting pressure on the underlying mantle. As a result, that underlying mantle is more likely to melt. Away from a mid ocean ridge, there's more pressure on the underlying mantle. More pressure means that the material is much less likely to melt. So, decreasing pressure can allow magma to form. Second, increasing the temperature. Well, that'll cause things to melt as well. So, an increase in temperature can cause materials in the asthenosphere to melt. And this can happen at what we call a hotspot. Thirdly, an increase in the amount of water in the asthenosphere can also lower the melting temperature of the materials there. This can happen at areas like subduction zones. We'll see some diagrams to help us explain this later. So, these three conditions decreasing pressure, increasing temperature, and increase in the amount of water can happen at plate boundaries. As a result, that's where most volcanoes are formed. At subduction boundaries, here one plate moves underneath another. If we've got an oceanic plate moving underneath a continental plate, well, that oceanic plate, as it moves underneath, it will drag a lot of water with it. So all that water is subducted. The extra water in the asthenosphere can lower the melting temperature of the materials down there, leading the rock to melt and magma to form. And that magma, of course, is less dense than the overlying materials, so it will work its way up to the surface, and it can flow out onto the surface in a volcano. So that happens when an oceanic plate goes underneath a continental plate at a convergent plate boundary, but it also occurs when you've got two oceanic plate boundaries that meet. Here we've got one oceanic plate going underneath another oceanic plate. Same thing. This is going to bring a lot of water with it. The increased water can lower the melting point of the materials underneath, and the magma will bubble up. This can form what's called island arcs, or small islands in the middle of the ocean. So we also have volcanoes that form at divergent plate boundaries. Here, two plates are spreading apart. The place where they're spreading apart means there's less weight on top of the asthenosphere, meaning less pressure, which means that the melting point can be lowered and magma can bubble up. Also, there's often higher temperatures, so more magma can form there as well. Iceland is a good example of where the mid-ocean ridge is above sea level, and you can see it in this photo here. And the third place where we see volcanoes is over hotspots. Not all volcanoes happen at plate boundaries. Instead, some occur over hotspots. These are areas of volcanic activity that result from plumes of hot solid material that have arisen from deep in the mantle. A hotspot will stay at the same place even as the tectonic plates move over top of it. Do you recognize the islands in the photo below? Well, that's the Hawaiian Islands. And these are examples of islands that have formed over hotspots. So they're in the middle of a tectonic plate, and they have formed over hotspots. Here's what's happened. Between about 5.3 and 4.9 million years ago, the island of Kauai formed over the hotspot. So molten magma bubbled up, reached the surface, solidified, and formed the island of Kauai. But that plate that was sitting over the hotspot kept moving northwest, and as it did, it moved the island off the hotspot, so Kauai stopped forming. The next island to start to build up was Oahu, and that was created between about 3.8 and 2.5 million years ago. Again, after the rock hardened, those tectonic plates kept moving northwest, um, and Oahu stopped getting bigger. And then the next islands formed along the chain. Right now, it's the big island of Hawaii that sits over the hotspot. It's actively getting bigger right now. Um, but eventually, it will move off the hotspot and stop forming, and we expect a new island will form afterwards. So, Hawaii. This is one of those places where people live, people visit. It seems like a nice place. But some volcanoes you don't want to be anywhere close to. Some volcanoes erupt really violently, while others, like the ones in Hawaii, are a lot calmer. What causes the difference? Well, it all has to do with the type of magma. Silica is the primary ingredient in all magmas, and it determines a magma's viscosity. Think back to our first unit on rocks and minerals. Silica is the building block of quartz. And any minerals that have a lot of quartz in them, or a lot of silica in them, are going to be a lot more viscous. They don't flow very smoothly. If there's less quartz or less silica, the magma will flow more easily. So, more silica, more viscous. On top of that, magmas also contain gases. Most of this is in the form of water vapor and carbon dioxide. These gases are trapped in tiny bubbles when the magma is rich in silica. And that means that when they erupt a lot more violently. So we've got kind of three different categories of magma shown here. We've got the basaltic magma. This would be the most mafic. It's got the least silica in it. It's got the lowest gas content. It's the least viscous. It flows more smoothly. Its eruptions are rarely explosive, and it's got the highest melting temperature. You find basaltic magma places like oceanic hotspots and rift valleys, like the Mid-Atlantic Ridge, where Iceland is. So consider that the rift valleys like Iceland, oceanic hotspots like Hawaii, these are places where, despite the fact there's volcanic activity, people still live there. And that's because these eruptions are less explosive. On the other hand, we have the rhyolitic magma. These are the ones with the highest amount of silica in them. So this would be the most felsic of the magmas. It's got the highest gas content because the quartz or the silica traps the gas bubbles more easily. It's the most viscous of the magma. It does not flow easily. Its eruptions are usually explosive, and it's got the lowest melting temperatures. You find rhyolitic magma in the middle of continents. So if you've got a hot spot underneath a continent, you're way more likely to have very dangerous eruptions that are very, very explosive. And we'll talk about what's going on in Yellowstone in our assignment later on. Then we've got the intermediate and acidic magma. And this really is kind of halfway in between everything. Sometimes these eruptions are very explosive and can be quite dangerous as well. Mount St. Helens, which is probably a volcanic eruption that your grandparents or your parents might even remember, happened, I think, in the early 80s. In Washington State, just south of Vancouver, and was very, very explosive. My parents tell stories of ash landing in southern Alberta and covering vehicles. So each type of magma tends to form at specific locations. You've got that basaltic, the most mafic of the mineral forming at rifts and oceanic hotspots. It's less dangerous, and the andesitic magma tends to form at subduction boundaries. Rhyolitic forms where you've got hotspots under continental plates. As a result, it changes how dangerous each of these types of volcanoes can be. Then for lava flows, these basaltic flows, the more mafic ones, are associated with less explosive eruptions. As they cool, they form, as the name would suggest, basalt, super mafic, right? And the temperature and speed they flows affects the appearance as it hardens. Um, those who live in Hawaii, or the natives to Hawaii, have very specific names for these kinds of lava. Um, because they have to face them and deal with them all the time. The because it literally hurts when you step on it, is the very pokey kind here. And then the pahoho is the smoother, kind of ropey looking stuff that you see in the lower part of the photo. Pillow lava forms when lava cools underwater, and you do really get these big bubble formations, and that can be preserved for very, very long periods of time. There's some of this preserved up near Thunder Bay as well. So, um, volcanoes don't only make a mess, they also make beautiful landforms that you'll see around the world. The first kind of landform, as they mentioned in the National Geographic video, was the shield volcanoes. Shield volcanoes tend to form from basaltic lava. Remember that this is the least viscous lava, so it can flow a long distance before hardening. Layers of the magma build up, or the lava build up one on top of another, and it ends up having like gentle sloping sides and a really broad base. Um, we'll take a look at some photos of this later. Then we've got the cinder cones. These form when molten lava is pushed up into the air from a vent. As it falls, the lava fragments break up before they hit the ground. You'll get cinder cones that are entirely made up of scoria or pumice, those very vesicular rocks that we looked at in our first unit. Cinder cones tend to be a lot smaller, and they tend to form in groups on the sides of larger volcanoes. But you can get cinder cones like entirely made up of pumice or scoria. And then we've got the composite volcanoes. These tend to be a lot more steep-sided, and they develop when layers of materials from one eruption after the next starts to accumulate around a vent. These can form at subduction boundaries and can be very dangerous. Mount St. Helens would be an example of this one. Then we've got calderas. This photo is from Crater Lake in Oregon. You'll get these big round basins called calderas, and sometimes they fill with water, making caldera lakes. Okay, take a look at these photos. See if you can determine what type of volcano you think you're looking at. The first one, did you guess a composite volcano? You can tell it's composite because of its much steeper sides compared to the lower photo, which is a shield volcano. You can tell it's a shield volcano based on its less steep sides. And then here we've got another photo of a cinder cone. Okay, from here you'll go on to complete an assignment about volcanoes.